In this video, I'm going to talk about orbital motion. I'm going to use Newton's universal law of gravitation and talk about satellites around planets. Like always, I'll start with some theory and then end with some solved problems. Please take a moment to read the success criteria of what I plan to cover. So let's talk about what I mean by a satellite. Typically, I just mean anything of a smaller mass that orbits around a larger one. So this could be the moon around the Earth, or a television satellite, or even the Earth around a sun could technically be like a satellite. Don't forget that when we talk about these forces, they're equal and opposite thanks to Newton's third law. And we kind of have to talk about Kepler's law here, because he tells us that planets should be going around the sun in an ellipse, but we're going to simplify that and talk about it as being a circle. And the reason for that is so that we can talk about centripetal motion. Okay, so here we go. I have the equations here from our data booklet about centripetal motion. So remember, centripetal motion is caused by a net force towards the center of a circle. And it's not a force of its own, but something else has to cause it. And in this case, we're going to have the force due to gravity causing that centripetal motion. Now, I only have here acceleration, but this is a net force we're talking about. So I can just say F times ma, Newton's second law. And if I multiply this by the mass of the satellite, I will then get the centripetal force. Now, if I use it with this first part here, I can calculate then the speed at which it would be traveling in that circle. We'll call that the orbital speed. Note, because we're talking about this as a circle, we also can say this will be a constant speed. So let me introduce one more phrase, an orbital period. Remember, a period is the time it takes for one complete cycle, or in this case, for one complete orbit. And we know that this is going to be a constant speed. V equals the distance over time. And in this case, the distance is going to be 2 pi r. That's just the circumference of the circle. And the time would be the orbital period. Now, a very special type of satellite would be a geosynchronous one. And geosynchronous, so geo being the Earth, synchronous being the same time, means it's going to be over the same place at the same time as it orbits the Earth. You might think, well, why would that be important? Well, if you think about a TV satellite, they're aimed at the same place all the time. It doesn't change over the day. Whereas if we had a weather satellite, or maybe a spy satellite, it's going to be over a different area all the time, so it can get multiple different readings across the Earth. Now that we've gone through the theory, and before we get to the questions, has this helped you? Consider helping me out by telling your friends about the videos. Consider subscribing or liking the video. Thanks for your help. So now that we have our terminology of what a satellite is, how it's moving around, let's do some examples. So the first one here, we've got a satellite of mass m in a circular orbit around the Earth, and it's at a height h above the Earth's surface. And that's usually a really big, important part for you to think about. Is this the distance from the center? Because remember, centripetal motion would be from the center of the Earth to the center of the satellite. Or is it just the height above the Earth? Write an expression for the centripetal force needed to maintain the satellite in the orbit. Well, from our centripetal motion, I'm going to use one of those equations. I'm going to use the very first one. So mass times centripetal acceleration, which will be mass times v, this would be the orbital speed, over r. And in this case, it's going to be the radius of the Earth, which they said was capital R, plus the height above the surface. B says write an expression for the gravitational field strength in the region of the satellite. So gravitational field strength, if you remember, that's little g. That should be the force due to gravity over its mass. In this case, the force due to gravity will be gm1, m2 over the distance squared, which was r plus h squared. And don't forget, this m would be the mass of the satellite, So we're going to be left with gm being the mass of the Earth over r plus h all squared. Part C, use your two expressions to show that the greater the height above the Earth, the smaller the orbital speed. So the centripetal force is going to be caused by the force due to gravity. I'm going to put those two things equal. So our masses of the satellite are going to cancel out here. And I need to rearrange this. Oh, I'm going to be able to cancel out this square and all of this. And now let me just clean up the algebra for v squared. So here's my speed, and notice the height above the Earth's surface is right here on the denominator. Now this is not directly a v squared is proportional to 1 over h, but it does show that as my height here increases, that since it's in the denominator, my velocity will decrease. One thing I'm going to point out is, remember, we have to have the force due to gravity causing the centripetal acceleration. And yes, as I get farther out, the orbital speed will decrease, but don't forget about centripetal motion. If the speed decreases too much, remember there might not be a perfect vacuum right there. There might be still some of the Earth's atmosphere causing it to decrease in speed due to friction. It could then start falling towards the Earth. This would be like spinning a bucket full of water around. If you don't go fast enough, then when it hits the peak, there's not going to be enough speed to cause enough centripetal acceleration for it to keep going in a circle, and it would just fall. Let's do another example. We have the Earth and its radius given to us. Many places might have this in the data booklet, but it's not in ours. We have the orbit of the Moon with its mass, and it says it's in a circle of approximately 60 times the radius of the Earth. Show that the orbital speed of the Moon around the Earth is approximately 1 kilometer per second. Please notice those units. Now this equation is actually shown in the higher level section, but let me show you how to get it anyway. We know that the centripetal force is going to equal the force due to gravity. I'm going to use my mv squared over r for the centripetal force, Newton's universal law of gravitation, and I'm using capital M, little m here, and some places use m1, m2. It really doesn't make a difference as long as you keep track of which ones you're using. And an r squared here with the r, so v is going to be the root of gm over r. Now if I put these numbers in, because this is a show that question, so you have to show the full substitution as well as an unrounded answer. This was going to be 6.67 times 10 to the minus 11, and the mass of the Earth. And it says it's at 60 times our radius. And if I pick up my handy dandy calculator, I'm going to get 102 meters per second. Remember, unrounded answer because I need to show that it rounds to this. And the units here say kilometers per second, and I've written meters. Oh, the same thing. So I'm going to write this first unrounded in my new units to show that I know how to change them. And it's approximately what we've been asked for. Part B, hence confirm that it takes then about 30 days to orbit the Earth. Well, remember we said it should be going around at a constant speed. And we're looking to show the time here. So if I rearrange that, I'm going to have distance over velocity. My distance is 2 pi r over the value I just found. I'm going to put it in meters per second here. 2 pi times our radius, which was 60, times the radius of the Earth. And I'm going to get, so let me just go through how I go from seconds to days. We've got this big, huge number. Remember, I've got more significant figures than I need. I really should only have 2. Now this is seconds. I know that there is 60 seconds in 1 minute. Notice how I've written them so they can cancel out. I know that there are 60 minutes in 1 hour. I know there are 24 hours in 1 day. So what do? I pick up my handy dandy calculator. I take this number times 1 times 1 times 1 divided by all of, in brackets, 60 times 24. And when you do that, I'm going to get 27.4 days. Now, there's my unrounded answer. This only has one significant figure, which is approximately 30 days. So, please read the success criteria one more time, and hopefully you can say yes to both those points.